Good evening, guys. Am I audible?
Yes, sir.
Thanks. Okay, so we have been talking about the analogy methods, right? In the last lecture, we discussed transducers, and that was basically taught or presented by Dr. Sneha. And last to last lecture, I talked about the mechanical electrical analogy method. And like I mentioned in that class, that there is one more analogy method which is called membrane analogy for torsion. So we'll discuss that topic today. So okay, membrane analogy for torsion. Okay. So again, as I mentioned about this topic before, that this particular analogy method is basically what we essentially do, that we try to relate deflections of a membrane to the torsion of a particular shaft. Okay, and particularly this particular analogy method is actually specifically useful for shaft of non-circular cross sections. So you can have a shaft. So basically, what we talk about, torsion of a shaft. Okay. And this is how we also define a particular structural element. So when we talk about a bar or axial bar, we basically mean that a bar which is taking care of axial load, right, or which is having axial deformation. Similarly, we define shaft. Shaft is defined on the basis of how it basically takes the load. So shaft generally takes the torsional load or torque. So that is why we basically uh, discuss that the torsion of shaft. Okay. And if you talk about the another fundamental structural element, which is beam, beam is supposed to take the transverse loads, right? This is how this. So we have bar, we have shaft, and then beam. These are fundamental structural elements out of which you make your structures, whether it is your aircraft or whatever. Okay. So a bar is basically defined because it is taking axial loading. So this is, they are also called axial bar. Shaft is a structural element which takes care of torsional loading or torque loading. And then beam is basically taking care of transverse loading. Okay. Other than these three fundamental elements, we also have the other two other fundamental kind of structural elements that are basically a string or a membrane, right? So a string which takes care of tensile loading, right? And that is kind of a kind of derived version of a bar. And then you have membrane. The membrane is supposed to take the tension kind of loading. It doesn't take the transverse loading. Okay, so membrane is basically a string in two dimensions. Okay. So these are the kind of structural elements. So we have a shaft. We talk about shaft which will take care of torque loading or torsional loading. And then we have this membrane which basically takes care of tensile loading in two dimensions. So basically this is subjected to tension in two dimensions. Basically two dimensions which are along the membrane, not across the membrane, okay? Or not perpendicular to the membrane. Okay. Okay. And as I mentioned, membrane analogy for torsion and why we need this particular analogy method. because if you study torsion of a shaft of circular cross section, you have well established theories, and even experiment wise also it is easier to analyze a shaft which is having circular cross section. But the moment you have a shaft of non circular cross section, then it becomes difficult to analyze a non circular cross section shaft using your theoretical methods, even your experimental methods. Okay, so it is very difficult to study a shaft of non circular cross section, whether it is theoretical method or whether it is experimental method. So it becomes easy when we do the membrane analogy. So that is what we are going to discuss today. First thing we have to discuss, like I mentioned, analogy is established when you have similar governing equations, right? So there will be a governing equation for membrane, right? So there will be a governing equation for transverse deflections of a membrane, and then there will be a governing equation for torsional torsional stress function. Okay, so when you have these governing equations, what you see is that the governing equation for the membrane, right, and governing equation for this torsional stress function, they are actually same. They are basically similar, and that is why, because they are similar, you can basically make use of this analogy between transverse deflection of the membrane and torsional stress function for a shaft. Okay, so let us do this. So we'll first derive the governing equation for the transverse deflections of a membrane, and then we will derive the governing equation for torsional stress function for a shaft, and then we will see what are the governing equations we are getting, and then we will basically formulate the analogy between both of them. Right, we'll see what are the parameters which are similar in both of these cases. Okay. So we'll do this part first, the governing equation for membrane. Okay, so we will basically derive governing equation for transverse deflection transverse deflections of a membrane. Okay, and the other thing which I need to add here, transverse deflections of a membrane which is under pressure. Okay, so you have some 2D membrane, and from one side of the membrane, the membrane is basically going to be fixed around its edges, right? And then you apply pressure, and because of the pressure, it is going to have transverse deflections, and that is what we want to formulate. Okay, so first we will define what membrane, what basically I have already mentioned this part, but let us just write what is membrane, right? So let us define membrane. So membrane is something which is having very small, very small thickness, very small thickness in comparison to surface dimensions. This is the definition of a membrane. Okay, the surface dimensions. are basically significantly, very significantly higher than the thickness of the membrane. So it's basically paper-like structure. But even a paper should have a large surface dimension, then only we can define paper also as a membrane. Okay. Now the characteristic for a membrane is going to be, so this is going to have negligible bending rigidity. Okay, that means the the transverse stiffness or bending stiffness is basically very small. It cannot sustain any transverse loading. If you apply any transverse loading, it will just basically deflect, and it cannot take any load uh, in the perpendicular direction with respect to the surface dimension, or in the thickness direction. So if you apply a load in the thickness direction, it cannot take. Okay, and so to write that also, so it's basically a membrane membrane carries load via a constant tensile force along itself. Okay, so it can take loading along itself, basically along the surface dimensions. That is the basically thing here. So it can take constant tension force along itself. Okay, so it can only take tension force. Since it is a membrane, this is a 2D structure. So if you define this surface dimension in xy plane, that means it can take tension force in x direction and y direction. So this is the kind of definition of membrane. Now let us consider. Now we'll consider a membrane under pressure, and then we will derive the differential equation of motion for the membrane. So considering a membrane of non-uniform shape, okay, non-uniform shape, and it is fixed at the edges always. Okay, so we will consider one. This is a kind of membrane, and this is basically fixed. Let me draw a better one. So it's not circular. Okay, so we are considering a membrane of some non-circular shape. That is the funda here. So something like this. Okay, and this membrane is fixed at the edges. And let us take somewhere here as the origin of the axis in which it is defined. So this axis, this is y-axis, let us say, and this is x-axis. Okay, and then okay, and then with respect to x and y axis, there will be g-axis. So g-axis is out of phase. Okay, so this is g-axis is perpendicular to this membrane out of phase. So this is the axis system in which we are defining this membrane. And then if you take some part of this membrane somewhere, so let us take this part. Okay, At this particular element of the membrane, you will have tension force, and that tension force is denoted by N. Okay, so this is sort of top view. Okay, so what we have here, that you have a membrane which is fixed at the edges, and you're applying the pressure, and because of the pressure, it is going to deflect, and because of that deflection, transverse deflection, out of the phase in positive g direction, you are going to, because of the deflected shape, there will be tension force which will develop, and that tension force is basically your N, which I am showing on a small element of the membrane. So you have this N, which is your constant tension force, per unit length. Okay, and this constant tension force is going to be in both x and y direction. Okay, if it were a string, then it will have, you generally have the tension force along the string. Now we have a membrane which is basically string in 2 dimensions. So you are going to have a constant tension force in both the directions, x direction and y direction. This is the tension force. This constant tension force is basically along the membrane, okay, or in the xy plane. Okay, so we are showing the top view of this. We will see the side view of this. Okay, so let us see how it will look in the side view. So we have the membrane. We have this membrane which is basically fixed. So from here to somewhere here, and you are going to, so this is your membrane. Okay, and let us say somewhere here is the center, and so we are talking about side view. So this is your, let us say, y axis, and then this will be your g axis. And what you are doing here, actually, you are applying a pressure. So this is the pressure. So pressure, let us say pressure pi you are applying, and because of this pressure, this is the deflected shape of the membrane. Okay. And then how, so we are basically showing this in yz plane, so side view in yz plane. Okay, and then similarly you will have the same thing in the xz plane also. So this tension force, right, so if you have the tension force, so you will see that then this tension force is basically along the membrane. So if we talk about this point, you will have a tension force along the membrane, which is here, and similarly if we talk about this point, you will have along the membrane tension force N. Okay, and if you consider this surface is going to have deflection. Okay, function of x and y. Right? So this is the displacement of membrane in g direction. Okay, if you do the side view in the xz plane, you are going to see the same thing. So you will see, and basically it's like this. Okay, so now we have the membrane. We have defined the membrane. We have also shown that how it is basically deflecting because of this internal pressure Pi. And we have seen the top view. We have seen the side views. Now we will proceed with the proceed with the equilibrium equation uh, derivation. So for that, we will basically do some assumptions. So let us say assumptions. So first assumption is basically we will consider a small W, a small displacement. So we are not having a very large displacement for the membrane. We are talking about small displacement, and because of this, the this is true basically, so that the constant tension force, the tension force N is constant. If you consider very large displacement for the membrane, then this assumption will not be valid. This tension force in the membrane will not be constant. It will vary along the membrane. Okay. Now we will consider equilibrium of a small element, or component of the membrane. Okay, so we will kind of, so like we do in the typical strength of material this process, right? So we take element of out of a body, and then on that particular element we basically indicate all the possible forces, and then we apply the force equilibrium equations. Okay, so we are basically talking about something like this. So this is the kind of element we are talking about when when the membrane is deflecting. During that deflected shape, somewhere here we can take this element. So let me just show that. So we have some element like this. This is the small element. So this is exaggerated view of the small element out of membrane. Okay. So okay. So on this membrane element, so let us denote the axis. So we have these axis systems. So this is your y-axis, and then we have the x-axis here. And similarly, we'll have x-axis here, and then we'll have x-axis here, y-axis. So we have this x-axis both sides. Okay. So because of this, the deflected shape, for this deflected shape, so we will have something like this. Okay. Along this line, we have to basically mark. We have to basically mark the tension force. So there will be tension force along this line, and this tension force is going to be. So if you consider the length, so let us consider the length in y direction. So this is your length in y direction, dy, and then similarly we have length in x direction, which is dx. Okay. So if we have constant for this tension force n at this point, this is going to change over the length dy, and this will be, so this is the tension force here along the, so this is the tension force like this. And this, if it is n here, it will change over length over the length dy, and this is going to be, so this tension force is going to be n here, and then similarly we are going to have this. So okay, so tension force along x-axis both side. Yeah. Okay. So like I mentioned, so over this small element, this is a small element, and we have already said that the tension force is going to be constant over the membrane. So even for this small element, the tension force is not going to change. Whether we start from this side to this side, tension force is going to be same. Similarly, starting from this side to this side, tension force is going to be same over this small length dx. Now, this is the deflected. This is the element which is coming from the deflected shape of the membrane. That means this is kind of a, so if you talk about the angle here, right? This is the deflected shape. So at this particular point, this is the slope with respect to x-axis. So this is the, if you talk about this is the slope of the deflected shape. And to define that, this is basically your del w upon dou x. Okay. So if this is the slope, right? Slope, how do we calculate? If you consider the slope along the x-axis, this is going to be, w is the deflection. So w, this is going to be dou w upon dou x, and similarly it is going to have slope, and this slope basically will be changing over this element. Okay, so if this is the slope at this side, this is going to be dou w upon dou x plus change over length dx of this same thing into dx. Okay, similarly you are going to have slope this side, and this slope is basically your dou w upon dou y. So it's slope in y direction, and then similarly you are going to have slope, and this slope is changing over length dy, and this is going to be dou w upon dou y plus first order change we are considering, so it's going to be dou w upon dou y into dx. So what we have, so dou w upon dou x is the slope along x-axis of the deflected membrane. Similarly, we are going to have dou w upon dou y. This is in y direction. Okay. And you have this constant tension force, and which is not changing. This is same at all the sides of the this small component. Okay, and then the other assumption here is dou w upon dou x, which is slope in x direction, slope in y direction, are also small. Okay, so these assumptions will be helping us when we derive this governing equation. So now we will basically talk about, so this is the top view of the selected component on which we have marked the force constant for tension force n, and we have also marked the how the slopes are going to change. Okay, so dou w upon dou x is the slope at this position. This is going to change to dou w upon dou x plus dou upon dou x, because this is the x direction change, right? So this is going to change from here to here over this length dx. Similarly, this slope is going to change over the length dy, and we are considering first order change for the both sides. We can now, for convenience, we can consider the side views. So let us consider the side views. Side views of the small element. Okay, so let us consider. So this is the deflected membrane element at this point and this point. So this is in YZ plane. This is in YZ plane, and this is this YZ plane. Basically, this is your Y direction, and similarly, this is your Y direction. Okay, and then perpendicular is your G direction. So this is your G direction. So with respect to this node, you are going to have, for this component there will be a tension force. There will be a tension force here, and similarly there will be a tension force here, and both are going to be same. And so we are this is Y direction, so we can consider slope in Y direction. So we will have slope, and then this slope is dou w upon dou y. Okay, and at this side the slope is dou w upon dou y plus dou upon dou y, dou w upon dou y into dy. This is the slope, basically your angle, and with the help of this slope we can actually resolve these forces. So we can resolve this force, and we can also resolve this force. Okay, and we are going to implement the force equilibrium in G direction. So we will basically get the G component. So the G component, so this is the slope we have, dou w upon dou y, and this is the direction in which n is acting. So we are going to have n, it n into sine of the slope or angle, that is your sine of dou w upon dou y. Similarly, we are going to have the component here, and this component is going to be n into sine of this angle, sine of dou w upon dou y plus dou upon dou y, dou w upon dou y dy. Okay, so these are the forces in G direction we have obtained when we are considering YZ view, basically one of the side view, and similarly we can consider in the XZ. So let us consider the XZ view. This is going to have the same thing. This is your deflected membrane. XZ view, basically this is how we are considering. So this is your x-axis, both side. Okay. You are going to have tension force here. This is your tension force this side, and similarly this will be tension force here, both same. This side slope, it is going to be dou w upon dou x, or we are talking about x direction, and this side slope is going to be dou w upon dou x plus dou upon dou x, dou w upon dou x into dx. Now we can resolve this force n, so we'll have one force this side. This is going to be n into sine dou w upon dou x, and similarly we'll have n into sine of this angle, dou w upon dou x plus dou upon dou x, dou w upon dou x dx. Okay, now we have even marked these forces in the side views. So we have done the same thing, whatever we had here. This is kind of, we can say, top view, and we have done the side view representation. And side view representation basically help. We are going to implement force equilibrium in G direction, and we have all the forces, whatever are getting developed for this deflected membrane in G direction, except there is one thing which we are forgetting here, which is the pressure. So we are going to have pressure, pressure force. Due to pressure only we are getting this deflector shape. This is the Pi, and similarly we'll have for this P. This is Pi. Okay, and so dimension wise, we can so take this is the YZ plane. YZ plane means this is the dimension dy, and similarly for this element, this is the dimension dx. So your pressure Pi is basically acting over the whole element. So that means pressure is acting on area, which is multiplication of dx and dy. So pressure is going to act in G direction, and that force due to pressure is going to be Pi into area of the small element, and area of the small element is dx into dy. Okay, now we are ready to apply the force equilibrium. So implementation of force equilibrium in G direction. Okay, so forces in G direction equal to 0. Now the very first force and force pressure is acting in positive G direction. Positive G direction is upward direction or out of phase. So that is going to be, so let me write uh, positive G direction forces positive, and positive G direction is out of phase. So Pi is in positive G direction acting on dx and dy. Now we have for this case, so let me just write this. So we have sine dou w upon dou y, and we have already said the slope. We have said here these slopes are small. So if you take sine of these angles, like sine of this angle and this angle, since these are small, you can basically approximate them as the same. So this you can write as n into dou w upon dou y. Okay, and similarly we can do the same thing for the other cases. This one also we can write n into dou w upon dou x. Okay, so when we are considering forces for the YZ view, so we have one force here and one force this side, right? So we can write them, and let us. So what we have here, this is acting downward, which is negative G direction. Okay, so this is negative G direction. So this is a negative force. And this force is going to be minus n into dou w upon dou y, and this is force per unit length, and this is acting on what length? So let us go here. This force, this is the force we are talking about when we are talking the YZ view. So this force is acting on this length, and this length is basically dx. So this will be multiplied by dx. Similarly, for YZ, this thing, so we have this part. This, if you expand the sine of delta y upon dou y upon dou w upon dou y is going to be dou w upon dou y, and so on. So let me write it here. So what are going to have, and multiplied by the angle. Sine will not be there, so this will be dou w upon dou y plus dou w upon dou y square dy and multiplied by this is also acting at x. Okay, so you can come here. This is the force we are talking about. This is also acting at length dx from here to here. Okay, this was in positive z direction. Similarly, for the xz view, we will get minus n dou w upon dou x, and this is acting on length y plus n dou w upon dou x plus dou square w upon dou x square dx into dy. Okay, and summation of all these forces equal to 0. Now we can simplify this. So let me just write this after eliminating like terms and cancel out dx dy. Ultimately, what you are going to get pi plus n into dou square w upon dou y square and dou square w upon dou equal to 0. And finally, the final equation, governing equation is dou square w upon dou x square plus dou square w upon dou y square is equal to minus pi upon n. This is the governing equation. Okay, so this is the partial differential equation for lateral or transverse deflections w of x comma y. Okay, and the boundary condition. So let me write the boundary condition. So we have the equation. We also need to define the boundary condition here. Boundary condition is for this w, right? So w of x comma y is equal to 0 along the edges. Along the edges, or you can call it along the contour. Contour. Okay, so we have got the, let me just, so governing 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 partial differential equation for transverse deflection of the membrane. Similarly, we need, so if this is the equation for the transverse deflection of the membrane, we need the governing equation for the uh, shaft under torque loading. So that part also we will do, and then we'll see when we get the governing equation for the shaft, we'll compare both of them and we'll see that both of them are similar, and because both of them are similar, we can make use of the analogy method. Okay, so we are going to now, so torsion of prismatic shaft of non circular cross section. So just to define, so prismatic means that whatever cross section, so we are saying non-circular cross section, right? Whether it is a non-circular or circular cross section, prismatic means cross section uniform throughout the length. Whatever is the length of the shaft, starting from the bottom to the top of the shaft or whatever, from one end to the other end, the cross section is going to be uniform or same. That is the meaning of a prismatic bar. The cross section is not changing along the length of the shaft. So whether it is whatever is the shape of the cross section, circular or non-circular, it is going to be uniform along the length. Okay. And to derive the governing equation, we will make use of classical Saint-Venant's torsion theory. Okay. So let us draw one shaft. So draw one shaft here. So I'll try to make it of same cross section what or same shape of what we had for the membrane. That is the condition. The condition is we will basically derive the we will have a shaft of the same cross section of whatever we had the shape of the membrane. So whatever shape we have for the membrane, that shape is going to be the cross section for the shaft. So okay, still okay something. Anyway, this is arbitrary shape, but I'll try to just so let me go up. So what I'm trying to say, this membrane, whatever shape we have for this membrane, this is the shape which will be the cross section for this shaft. That is the condition. Okay. So this is the cross section of the shaft now. Now for this shaft, so let us say this is the total length. So this is going to be total length of the shaft L. L is the length of the shaft. And let us define the axis system. So this is going to be x axis. Then we'll have y axis. And then this is your j axis. J axis basically kind of the same whatever we had for membrane. J axis is your out of phase. Okay. And for this x and y j axis, so shaft means it will take torque loading, and that is what we are trying to study. So this is going to have a torque T. And because of this torque T, there will be deformation in the shaft. And because of the deformation, if you select any point in the shaft, that shaft can have tendency to deform in all three directions. So that's why let us consider displacement of a point in x direction u and displacement in y direction y v and displacement in z direction w. Okay, so when you apply this on this non-circular cross-section shaft, you apply this torque T, and because of this, so let us say, so you're applying the torque at top, and then bottom side this is fixed. Because of this applied torque, if you take any point in the shaft, at this point is going to have displacement in x-axis, in y-axis, and g-axis, and they are denoted by u, v, and w. Okay. Now let me just write the characteristic of this shaft. So length L of the shaft is significantly higher than x and y dimensions. Okay, you have applied a torque T is the end torque. Okay, and the displacement, so u comma, so you have u comma v comma w are displacements of a point in x comma y comma g directions respectively. Okay. Essentially, because of this torque loading, this is going to basically have a twisting effect along the length. Along the length, basically starting from this position to this position, there will be twisting in the cross section. And because of this twisting, at any cross section, if you take a point, suppose here, somewhere here, so somewhere here, so you take this point. This point is going to basically have u, v, and w displacement. We are considering w displacement, that is basically because if you take non-circular cross section, any shaft of non-circular cross section is going to have displacement w in the g direction, or the direction of the axis of the shaft. If you have circular cross section, you apply the torque for circular cross section, that w displacement is not there. Only in plane displacement will be there. So whatever position you take, suppose this is the section you are taking here and here. In this section, because of this torque, there will be only rotation of the section. The section is not going to have warping, and warping means section is not going to have out of plane displacement, and out of plane displacement is basically displacement in g direction. So that is not happening for circular cross section. But if you have a non-circular cross section of some arbitrary shape, even if you apply this torque, when you apply this torque T, there will be displacement in the cross section, and there will be displacement of the cross section out of plane direction, and that is the w displacement we are talking about. So for circular cross section, any point on a cross section will have only u and v displacement, but non-circular cross section is going to have u, v, and w displacement. That is why it becomes difficult to study non-circular cross section. Okay, so for this problem, we'll formulate some assumptions. So very first, each cross section, each cross section at g locations. So cross sections are defined along the length basically, and along the length you have g direction. So at g locations, each of these cross section will basically rotate just give me 1 minute. Okay. Okay, so we are going to consider some assumptions. So what we are saying is each cross section at G locations, they will basically rotate. Each cross section will rotate. Each cross section rotates as a rigid body. So that means no distortion of the cross section shape in x, y directions. Okay. So cross section is not going to change. That is the condition. Okay. So it's every cross section will just rotate, and that means even after torque you apply torque, there will be deformation, twisting deformation, and because of the deformation, we will basically again we are considering that the cross section whatever was there originally, it is not changing. We are having the same cross section. Second, so rate of twist, right? When you apply torque, you're applying torque at here. So this is the end torque starting from bottom, which is the zero position kind of. So starting from, so there, because of this torque, you are going to have twisting, and twisting is going to vary from bottom to the top. Okay, and variation of the twisting is basically rate of twist. So rate of twist is the how the twist is changing from bottom to the top surface. So rate of twist denoted by K is constant. Okay, this is not basically changing type. So whatever this rate of twist is basically constant. Starting, it is zero. Twisting is zero at the bottom, and twisting is maximum at the top. And the rate of change of that is constant. So so rate of twist. So basically, K is your d alpha upon dz. So and where alpha is your twist angle, is the twist twist angle. Okay, and of a cross section at position G. So you take a position G along the length. At that position, alpha is your twist. And then change of alpha with respect to G direction is your rate of twist. Okay. So alpha is your twist angle. This is basically equal to d alpha upon dz into the distance k into. So this equation basically says at g equal to 0, alpha is 0, which is basically consistent. From the bottom, at the bottom you have the fixed condition. At the fixed condition, you should have 0 twist angle, and that is what is your getting from this equation. And then the third one is basically cross sections. So cross sections are free to warp in G direction. Okay, but warping is same for all cross sections. Okay, so you can have the warping, which is warping basically that the displacement of a point in a cross section in the autoplane direction, which is G direction. That displacement is basically the other definition or other meaning of that is the warping effect. Only thing is that the warping is basically same from the bottom to the top. This is not changing. This is same from the bottom to the top or throughout the length. Okay. So let me just write. So warping is basically extensional deformation in the direction extension deformation in the direction of the axis about which the torque is applied. So we are applying the torque with respect to g axis. Okay, g axis is the along the length of the shaft. In the g direction, you can have extensional deformation, and that is basically your warping. External deformation of in a cross section of a point in a particular cross section. Okay, and this is, I'll just write common in the case of non-circular cross sections. Okay, so this is the torsion of whatever shaft we are considering of non-circular cross section, prismatic shaft. And we have defined the problem. Now we will basically proceed with the derivation of governing equation. We'll have to do it one by one. So very first thing we have to consider. So we are applying the torque. We have to first study how are the displacements basically coming into picture. What is the formulation for the displacement? So once you have the displacement, you can from displacement you can get the strain. From a strain you can get the stresses, right? And then finally you can basically use the formulation for stresses, and then we'll see further what we are basically what we are going to see. So so let me start one deformation. So you apply torque, and then you take a point, and for that particular point you study the deformation. So deformation of cross section due to torsion. Okay, so I'll try to draw the same cross section. No, it's not. So so this is the cross section we have. Okay, somewhat similar cross section. Then let us say here this is the this is at some location of a particular cross section along the length. Like this is at some location G. Okay, and this is your axis. This is your y direction, and this is the x direction. So I'm looking at the top view. Okay, and this is how we are applying the torque. Okay. So in y direction you will have displacement v. In x direction you will have displacement u. Okay, and let us consider from this. Let us consider this position, and let us add this particular position in the cross section. We can consider one element. Okay, when you apply this torque, this element is going to rotate, right? So let me consider like this. Okay, so this element is going to rotate like this. So there is a rotation. Okay, because of this torque, this element is basically point. And how do we define a point? We always take a very small element around the point of interest, and then we try to see how the element is basically behaving. So we have this element here, and this is basically coming to this position. Okay, this is the effect of flight torque. Because of this moment displacement, there will be displacement in x-axis, and there will be displacement in y-axis. Okay. So we can just do the exaggerated view of this. So let us say this angle, we are considering this as a beta angle. So this is angle beta, and this rotation is, let us consider this as alpha. So alpha is the twist. So this is the original position. This is the original position along. This is the line along the original position of the element, and this is from x-axis. We are considering beta because the torque. This is going to rotate, and this is going to have a twist angle, which is alpha. Okay, so if you consider a point here, so let us consider a point here. Okay, and this point is moving. So this point is going to move here. Okay, so this is the original location, this is the new location, and because of this, so what you are going to have, so this is along x-axis and this is along y-axis. So this is the, so what you can say, this is your displacement in x-axis, which is u, right? And this is displacement in p-axis. This is the uh, p point, and let us say this is p prime. This is how. Okay, so we need to find what is the value of u displacement, what is the value of v displacement in terms of these angles. So if this is angle beta, so with respect to this line, you will have beta angle here. Similarly, this will be your beta angle. Okay, and this is going to be, if this is the distance from here to here, if this is your distance r, this distance is going to be r. Sorry, so this is going to be r alpha, right? So considering the small alpha angle, so you can basically write this distance from P to P prime. So this is basically distance P prime, which is R alpha. In terms of this R alpha, we can get V and we can get U. Okay, and this is the cross section considered at some positions, at some G location. Okay, so as the alpha is changing from bottom to the top, alpha is going to change. You are going to have different twist angles, and because you are going to have different twist angles from bottom to the top, you are going to have different values of u and v, right? So what you have, so displacement u, which is function of x, y, and g. This is going to be, so u is going to be, this is this angle, we know this angle is your beta, and we know this distance p prime. So this is basically, and you can see that positive g direction in this direction, so this is positive x positive, and because of this rotation you have u, which is negative. So u of this one is basically r alpha minus of sine beta. Similarly, v x comma y comma g, this is going to be r alpha cos beta. Okay, so you are basically resolving distance p prime. So cos component is your v displacement, and sine component is your x displacement, and then your displacement in g direction. This is, like we mentioned before, this is only function of x comma y. Warping or displacement in autoplane direction is same from top to the bottom or bottom to the top. So warping is same, right, throughout the line. That is why this is independent of, this is independent of d direction. So w of xy is basically wxy. Okay, so if I define, so from this position, let me write O to P is, so OP, let me write OP is basically R, and this is equal to this distance. OP prime is also R. So that is what we have. So OP prime is, both of them are, and R is equal to, so if you write in terms of, so you can write it like this. So this is the distance x, and this is the distance y. So R is the square root of x square plus y square. Sin beta is y upon R, and cos beta is x upon R. So we have the values of R, beta, right? Sin beta and cos beta. These we can put here. Okay. And the other thing we already saw, that alpha is basically equal to d alpha upon dz, or into z, and d alpha upon dz rate of twist, which is k into g. So alpha is equal to kz. So all of this, these entries and these entries, if we do, we'll get displacement x comma u of x y z equal to minus y k g v equal to x comma y comma g x k z, and y, sorry, w is w x comma y. Okay, so we'll have to eliminate this part, and we'll see later how to do it. Okay. So we have now defined the values of the displacements, right? So when you apply the torque, there will be deformation. If you consider a particular point, that is going to move because of the torque loading. Basically, it is going to rotate, and because of the rotation, we have obtained the displacements u, v, and w is independent of g. Okay. So we can see that displacement u is function of g, and similarly displacement v is also function of g, and other position xy and rate of twist. From these displacements, now we can try to get the values of strain. So we'll use strain displacement relations, and this one is, now it is simple. So first we'll talk about normal strains. Normal strains epsilon xx, strain in x direction, is simply whatever displacement there is u in x direction, which is u, differentiation of that with respect to x. Okay. And similarly, we are going to normal strain in y direction. This is going to del v upon del y, and epsilon gg is going to del w upon del g. Now let us see. So we are differentiating u with respect to x. You can see that there is no x in this. That means normal strain in x direction is equal to 0. We are differentiating v with respect to y to get strain in y direction. You can see there is no y here. This is also 0. And w is anyway independent of g. So this is also 0. So all three normal strains are 0. Now let us talk about shear strains. So shear strains. So epsilon xy is basically going to del u upon del y plus del v upon del x. Okay, implementing this. So u is a function of y, v is a function of x, and you are going to get minus kz plus kz, and then they are cancelling out. You get 0. So this basically says cross section does not change the shape. Okay, because there is no shear strain in xy plane, so cross section is not changing the shape. And this indicates that there is no normal strain in x, y, and z directions. Now, also there we have only one component of one shear strain. There are two more. So other shear strain. So let's talk about epsilon y z. This is going to be del v upon del z plus del w upon del y. And this will be kx plus dou w upon dou y. And then epsilon zx, this is going to be dou u upon dou z plus dou w upon dou x. And this is minus ky plus dou w upon dou x. Okay, so what we have here, that we have shear strain epsilon yz and epsilon zx, epsilon zx are non-zero. Okay, so there is, because in this case, so we have, there is no shear strain in the xy plane or along the cross section direction, but we have shear strain in the yz plane and zx plane. Yz plane and zx plane means these are the shear strains which are acting perpendicular to the cross section. Right, cross section is in xy plane, right? And when you apply the torque, and because of the non-circular nature of the cross section, and because of the existence of the warping, you have these shear strains in perpendicular direction, basically in z direction with respect to xy plane. Okay, and now we have obtained all the values of the strain. So first we obtain deformation, then we use a strain displacement relations. Now we have obtained the all possible all non-zero strain values. So we have two non-zero strain, which is one is epsilon yz and the other one is epsilon zx. Okay. Now next, the next part is basically use stress strain relationship and then find what are the values of the stresses, and then we will basically use a Prandtl stress function, which is basically uh, with the help of this whatever stress we get, and then we use Prandtl stress function, and from there we will get the governing equation. From then, after that we'll formulate the boundary condition. Finally, we'll get the governing equation for this torsion of the non-circular shaft, and we'll get the boundary condition. And then finally, we will be able to establish the analogy, and we'll see which parameter is corresponding to what parameter from the analogy. So I'm going to stop here. If there is any question, please let me know. Okay. So if there is no question, I'll see you guys in the next class. Bye.
Thank you.